So next topic, network flow. It's actually going to go very much into, I don't know if I'll answer why, but certainly fractional numbers will become very natural. Um, and right, so all this we just did. Right, so where we left off, right, the duality theorems still hold. The only issue is algorithmic when it comes to dealing with more general capacities. Okay, so, okay, so slight tangent for a moment. I'll bring it back to path packing. So we're going to discuss this problem called max flow. Maybe you've heard of it. Okay, but it's a lot like what you did. But imagine you're trying to send like water from S to T. It's like a liquid fractional version of path packing, and we'll make the connection more formal in a moment. Okay, but the idea is you want to interpret the edges as like pipes of some capacity, and then you want to send as much, water through the system from S to T as possible. Okay. All right. So that means we want to instead of like so maybe one thing that's a little different than what we're used to is is up to this point we've always been doing extremely discrete decisions. Right? What is the shortest path? Find me a path, find me a Hamiltonian path, pack paths, find me a spanning tree, edit distance. They're just very discrete. But this time, since you're trying to figure out how much water you could send from S to T or electricity or flow through a network or whatever, you're now going to be sort of like determining fractional values. Okay. So what we're going to do is we're going to try to compute some kind of flow vector, which is to say, for every edge, I'm going to assign some non-negative value that represents how much kind of liquid or flow I'm pushing through that edge. So it could be like 0.1 units, 0.3 units, 1 unit, so forth. Okay, but it's going to be represented by, I'm just imagining having like an array, one entry for every edge, and some number there. So now I want to also come up with some mathematical rules to try to model our problem. Okay, and maybe you guys would be able to come up with it. So first of all, the rule is, you can only send flow in the forwards direction, and you're not allowed to like exceed the capacity. So how would I write that down mathematically? It's not deep or anything, just how do we express it? Sure, just any equation. The sum of all capacities should be less than something. Uh, so it's going to be something like that. We want to do less than equals. That's what I'm looking for. But yeah, C's are capacities. There's how much you can take. F represents how much you are taking on each edge. Do you want to put some constraints on F? You're not allowed to just take as much as you want, stuff like this. Yeah. Yeah, so F needs to be less than equal to C for every edge. Also, F needs to be non-negative because you can only push. Okay. So let's say that if you're allowed to, I thought I erased this. Maybe I did. Okay. So, oh, my pen's not doing so well either. Uh, okay. Sorry about that. Okay, so 0 less than equal F of E less than equal to C of E. But it's just saying you can only take flow up to capacity. Okay. Okay. Now you can't just like well, that doesn't fully describe. So that's not the only rule we need. So I'm trying to send water from S to T, and imagine like I can't just like put like 10 units of flow on this pipe and then only 2 units of flow on the next one, because where did those 8 units of flow go? And stuff like this. right? So water can't disappear. It can go into the system at S, it can leave the system at T. Okay, but in between, for each vertex, what goes in must match what goes out. Okay, so there we'll get some summations. Okay, so here we're going to get something like, if you have like 1/2 unit of flow here and 3/4 units of flow here going in, and then maybe if you have like 1/4 unit of flow going out, and then how much flow has to go out the other? Like 1. What goes in has to be what goes out. So maybe looking at this like example graph on the right, maybe you have some kind of flow that sends 1 here, and then like 0.5 along here, 0.5 along here, 1 unit here. We'll split it up into 0.5, 0.5, 1, 0.5, 0.5, 1 or something. Here's assuming all the edges are unit capacity. But you can see the water splitting and joining, but the overall mass is conserved. Okay, so those are our constraints. And our goal is to send as much flow from S to T as possible, subject to these constraints, which, I don't know, sometimes writing down the equations might throw people off, but they're very intuitive, right? You can only use up the capacity of the edge, and what goes into a vertex must be what goes out. Okay, so as far as the objective goes, how can I try to express the objective, trying to send as much water as possible, in some mathematical notation as a summation of stuff? Yeah. Yeah, so if I just want to know how much water is going through the system, I can just look at the faucet, how much water is coming out of the source. Okay. One thing you do have to be careful about is you want to look at the net flow coming out of S. Maybe the flow is doing something silly where it's piping flow back into S, but it goes back out. So that's why we have a subtraction. Okay, but I'm summing the flow that's leaving S minus the flow going back into S. Okay, so that's a net flow going out of S. We could have used T instead. Okay, so this is your first, and maybe in this class only, example of a linear program, which is one reason why we covered this. Okay, so it's a linear program because everything is expressed as like a linear equation or a linear inequality. So I have some variables and I have some constraints. My objective is just summing up some variables. My constraints are like, oh, this sum of variables is at most this, that sum of variables is at most this. This sum of variables has to equal that sum of variables. Okay, so everything is just linear. Okay, and tons of problems. You can take some problem in the real world and try to write down some linear version of the problem. Okay, flow is a particularly well-behaved and intuitive one. It's a good place to practice some techniques that otherwise could carry over to, in general, analyzing linear programs. Okay, so how does max flow relate then to maximum path packings and minimum cuts? Any ideas? Like, is the value greater than or less than each other? How does the max flow relate to the number of paths you can pack? Let's say if the capacities were integral. Yeah. Okay, so max flow less than equal to path. Why? So one of these seem more flexible than the other. Oh, okay, let's see. Okay, so let's say that I have a path packing. Okay, it could be even fractional. So here I've set it up fractionally. I don't know if this notation is very good, but basically, okay, I should have maybe done this more carefully. Let's say this is the family of all paths from S to T. Okay, and X is some weighted combination. So I might say like, oh, this first path, I'm going to take one of them, and the second path, I'm going to take half of them, or whatever. Okay, but still subject to capacity constraints. The total amount of path using some edge is at most the capacity of the edge. Okay, so that'll be a fractional path packing. Okay, how can I define a feasible flow from my path packing? You can also just say, let's just say we had a bunch of edge disjoint paths in the simplest case with unit capacities. How can I get a flow for the same graph? I want to try to convert a bunch of paths into flow. So you want to come up with some F. No? Confused? Yeah. Okay, should F be the max? Oh, okay, so of all the paths using it, what's the largest value assigned to it? Okay, that's reasonable. Would that conserve? Will that conserve flow? I mean, would that? I think we should then be a little bit worried about this one. So let's say that you have some path that comes in. I mean, it's not clear that like the maxes of these edges are going to sum up to the maxes of the edges leaving. Okay, the other suggestion was the sum. Okay, so okay, the flow is just going to say how many total paths are using this edge, fractionally added up. If 5 paths use this edge, they each have weight 1 or something, then that can be a value of 5. Okay, so we can think of a flow as for any solution of the kind of path packing problem as reflecting how much of the edges are being used. And now we can double check things like the capacity constraint, right? So for the path packing problem, the capacities were saying, oh, only 5 paths can use this, right? Which means that you're going to only have 5 units of flow along that edge when you add things up. Okay, so capacity is more straightforward. What about the degree conservation? I want to make sure for my flow, what goes in is what goes out. But why? So all these paths go through the vertex. So if it's like a 0.2 units of a path, that's 0.2 in, zero point 0.2 out. If it's 1 unit of a path, 1 unit in, 1 unit out. And that will get added up to the flow. So you'll conserve flow. Okay, does that make sense? I feel like maybe the mathematics are getting us a little cloudy-eyed. Yeah. Okay, so some kind of Dykers kind of thing where starting from S until you get to T, for each vertex, how much flow can I send here? How much flow can I send there? How much flow can I send there? And gradually building out. Okay. So, uh, well, I think there's a couple things going on. First, you have to decide which vertex you're going to add next. Next, um, you kind of want to keep track of where the flow comes from. So maybe the flow like goes along an edge and goes to there, and so you get a big number here. And it goes to here and goes to here, big number here. But they're both using the same edge, right? And then you get some edge here, say, oh, I could send a ton from here and here. Now you're using this edge twice. So you'll forget where the flow came from, and you might be reusing edges. Okay, but anyway, so you can think of flow as some kind of fractional thing that's not that different from paths. Okay, okay, let's see if the next thing makes more sense. Okay. All right, now I want to try to relate the minimum ST cut to the maximum flow. Okay. So let's say I have S and T, and I have my set of vertices A. And let's look at the edges that leave A. Right, that's some ST cut. Okay. So the amount of flow that I can possibly send out of S, out of this set S, right? It can only use these edges. So the size of the flow, first of all, is equal to the net flow out of S, out of A. Just from this, what goes in. Originally, it's equal to the net flow out of S, but then if I pick any region around S, right, the amount that goes out minus the amount that's coming in, that'll give me exactly the amount that ends up at T, the amount that left S. Okay. And this is going to be bounded above by the capacity of that cut. Okay. So putting everything together, you'll get rats. We'll get the following. So we know that any maximum path packing can become, or any path packing can be converted into a feasible flow of the same size. That flow just writes down for every edge how much capacity is being used by the path packing. And on the other hand, you know that the max flow is bounded above by the min cut. And meanwhile, we already know that the extreme points are equal. Okay, so they're all equal. Okay, so why is this useful? Okay, so path packing and min cut make some discrete sense to us. Right? I can imagine, at least for discrete capacities, certainly min cut makes sense no matter what the capacities are. Maybe fractional path packing is a little confusing to think of 0.1 of a path, 0.2 of a path, but certainly discrete units of paths are straightforward, right? And this is just some continuous relaxation. So max flow turns out to be equal in value to all of these things. On the other hand, max flow in some ways might be simpler than path packing because I only have to remember the values on each edge. I don't have to keep track of all the paths that constitute it. As long as these paths kind of just satisfy, the capacities and what goes in, what goes out. Okay, so we're going to find it maybe algorithmically helpful to think about flow and so forth. Okay, you look upset. Okay. Okay, so that's our theorem. I don't know where I'm going with this. All right, so much for max flow. Now let's try to get a strong polynomial running time. If I get a running time for flow, that's a running time for path packing as well. Okay, so we're going to try to just generalize our algorithm. in the most natural way, the first thing we want is some kind of residual graph, right? And before we said, oh, if I took an edge, I should add the reverse back into the graph. And here it makes even more sense for flow. If I'm sending 1 unit of flow in this direction, I should always be able to undo and decrease the flow, right? Which is like pushing flow back in the opposite direction, right? So pushing flow back in the opposite direction could also just be interpreted as decreasing. So if I have 1 unit of flow going like this, I should add the opposite capacity to the graph. So it's just like adding edges, but if you're doing a fractional value, then you'll be adding a fractional capacity. Okay. Now, right, so if I have some edge with capacity CE, and I'm using FE, then you have FE minus CE capacity left in the forwards direction, and you add F of E capacity in the backwards direction. Yeah, you push 5 units forward, you decrease the capacity by 5, because you used up 5. But now you have 5 more in the opposite direction, because that would be like undoing the flow. Great question. Good. Yeah, should be CE minus FE. It'll be something like this. Okay, good. All right, so this was our algorithm before, and now we want to start changing it. We want to figure out how to get the maximum ST flow, right? Okay, so some of this algorithm still makes sense. We have some residual graph. You want to send flow from S to T. It is natural to still trying to find a path from S to T, and then maybe send flow along the path. Okay, so maybe the first step is okay. Now, how do I modify? So the claim take P and remove all its edges isn't quite make sense anymore. Maybe, so we have P, but ultimately I'm updating F, right? So how should I maybe try to express that? Yeah, so maybe what we'll do, right, well, maybe we'll just route flow along the path, and maybe a reasonable thing is to route as much flow as possible. Okay, so you find some path from S to T, it's using some edges that have positive capacity, but there's going to be some bottleneck edge, right? And saying, oh, what's the minimum, this edge only has capacity 1, so that's as much flow as you can send. So once you find this edge, you can try to route as much flow as possible. And then instead of sort of like adding reverse, we'll do this fractional version where we update the residual graph. We'll add capacity in the backwards direction. We'll subtract capacity in the forwards direction. Good. And we don't need to uncross anymore. We're not worried about paths. Okay. So, right. So we'll do something this. Now this is quite reasonable, right? And if it terminates, it'll be correct, kind of by what we've already done. But it might not be polynomial time. Okay. So I think I have an example. Okay, so a graph like this, right? What's the bad case? This is the integer capacities. What could happen that would be bad? Yeah. Yeah, you'll send 1 unit of flow like this, and then this capacity will become 2 to the 1 over 100, and this will become 2 to the 1 over 100. And this will now go backwards in the opposite direction with capacity 1. You send one more, send one more, send one more. You'll need 2 to the 101 or something, plus 1 iterations to get it all through. Okay, so these bottlenecks can be bad. Okay, any ideas of how to try to fix this? Try to find the path with the largest bottleneck. That will actually get a running time that will actually show up on your homework, because it'll actually get a funny running time that looks sort of like a logarithmic dependence on lambda. Okay. Yeah. Mm-hmm. Can you do a random path? Uh, okay. Well, okay, I think one thing that can make the random path tough is I can add a bunch of these like shortcuts that each have capacity 1 or something, relatively small, and they'll each sort of tempt you. Uh, would that work? Yeah, I'm not sure. I'm not sure how to analyze that either. Uh, yeah, okay. We'll leave that as an interesting idea, a random path. I can't confirm or deny it'll work, but I think it won't be, yeah. What you want to do is you want to set up like a lot of traps, to try to mess it up. Yes, I think actually if you do something like this, maybe if you add a bunch of like unit edges, like, so if you just add a ton of these, well, I guess, but then you have more edges to work with. Yeah, but if you have like a ton, then it gets harder and harder to survive. Even if I add just 100 of these edges, relative to the capacity of 2 to the 100, you'd have to like get lucky 100 times in a row to make sure you don't accidentally go down. Because as soon as you go down, you can only get 1 unit of flow, right, and you're screwed. So I think that'll make it tough. And I don't have to add too many edges because each one gives a coin flip and it gets exponentially harder. Okay. So random path, kind of fattest path was the first suggestion. Any other ideas? One. I'll put one on these little edges. So then if you take one, then you're throttled. Yeah. Oh yeah, who says you even have to route a path? Why not split and things like this? Um, that's not impossible, but it does get a little more complicated. Yeah. There are definitely more sophisticated algorithms that try to set up data structures so that once you find a path, you can kind of reuse some of the searching you've already done, which is sort of like resuming and splitting implicitly. Yeah, any more ideas? There's at least one natural idea that hasn't been suggested that would work for this one. We're trying to figure out how to choose a good path from S to T, a smart path. Any old path could get you in trouble. Fattest path is actually not bad, but it actually won't quite get us a strongly polynomial running time. Okay, so we're going to analyze shortest path from S to T. Okay, so seems redundant. Okay, yeah. So here, when we're looking at a particular path, we're going to try to get the shortest path from S to T. Okay, so this becomes our graph then, our algorithm. Right, while there's a path from S to T, find the shortest one, route as much flow as possible, update the residual graph. So you're implicitly updating this vector f along the way. All right, so good, good. Okay, so the algorithm is very simple. The only question is how do we analyze it? Okay? And So here we're going to have to do something very subtle. Maybe it's one of the more subtle things. So we're going to try to argue, okay? So as you're doing this, edges come, edges go from the residual graph, right? In some particular vertex, it might get cut off from S for a little while. Maybe it gets reconnected later or something. But we're going to try to argue that the distance, just counting the number of edges from S to each vertex V, never goes down over the course of the algorithm. So somehow, by focusing on shortest path, we're going to show that we're making progress in this sort of funny way. Implicitly, it's in a dual way, but that's a little harder connection. But yeah, so we're going to look at the distance from S to V in the residual graph and somehow try to argue that we're making meaningful progress for this problem. Okay, that's quite subtle. Maybe instead of proving the lemma right away, let's assume it's true and see why it's useful. Okay, so all right, let's look at our graph. Okay, and fix a particular edge from like U to V. Okay, so this edge is going to get added to a residual graph. It's going to get removed from a residual graph over and over the course of an algorithm. Okay, all right. So let's say you find a path, you route some flow, and that results in removing E. So what happened? What do we know about E in that case? If E got removed? Yeah, it was constrained. So first of all, it's on the path. It must have been on the path. So it's on the shortest S to T path. So it actually looks a little bit like the picture where it's really going forward through some breadth first search layer. Okay. And okay, so just by the fact that it removed, it was on the path. What does that tell you about the levels? If I say the level of the vertex is how many steps away it is from a S. Yeah, but well, what is it at that point in time at the beginning of that iteration? Yeah, we knew it was level U plus 1. Okay, just because it was on the shortest path. Okay. And now suppose that edge from U to V gets put back into the residual graph. Then what do we know? Or what was happening? The backwards edge must have been used. So the backwards edge was on the S to T path, shortest path, right? Okay, so you have something like this. Now what does that tell you about level U? It's level V plus 1, right? So it's actually kind of flipped from before. So yeah, these are the two things, right? When it gets removed, I know that level V is equal to level U plus 1, or at least, at the beginning of the iteration. And then when it's added back, we know level U is equal to level V plus 1, yeah. Or the distances aren't based on capacities, you're just counting edges. So the algorithm is dealing with the capacities when it's routing flow. In the analysis, I'm just going to focus on distance in terms of number of edges from S. The algorithm isn't really directly concerned with this. We're just trying to do something very clever to try to analyze the algorithm in a relatively indirect fashion compared to what we've done before. So it's like an unweighted graph? Yeah, just counting edges. Some of those edges might have teeny tiny capacity, and it doesn't matter. Okay, so, but this is just, counting edges, something's happening. Okay. Now, let's assume the lemma is true. The lemma says that those levels never go down, the distances never go down. Right, so first level V is equal to level U plus 1. Then level U is equal to level V plus 1. So in particular, the ordering must have flipped, right? So they flip order. First one is closer, then the other is closer. And if the levels are never going down, what does that mean about the levels? So you have this, and you know they flipped, right? But you also know that this never goes down. So it couldn't have been like flipped like this. It had to have flipped like this, maybe even like this or something, right? So just because they flipped, and I guess they flip again, right? You know that they're going up and there's some progress being made. Okay, so every time that this edge uh, goes up and down, we know the endpoints of the levels are going up. Okay. Now the maximum level is like n minus one because you only be n minus one edges away until it's infinity. Right? So each level can only go up how many times? N. So that means E can be removed and added back in how many times? N. So any particular edge, just by studying these hop distances, can only be removed and added back in n times. Oh, okay, so that's very helpful. Okay, good, good. All right, one more observation we need. I claim that every iteration will remove at least one edge from the graph. But why? Yeah. Yeah, because we're always routing as much as possible. So we're always routing until we delete an edge. Okay. So finally, that I claim we can bound the number of iterations in our algorithm now. What is it? Huh? Mn. Every edge can only get deleted n times, and every iteration deletes an edge. So we have Mn iterations. All right, so put that together. You have Mn iterations. How much time does each iteration take? M plus n. You find the path. Okay. Put that all together, you get m squared n. Okay. So this is quite more challenging than anything we've done before because we're claiming that we can get like the optimal thing with relative to all these fractional values. You know, if you're just studying our flow vector, it might be making only tiny improvements each iteration, right? Uh, but still, we can argue that it's going to take at most m squared n iterations. You wouldn't be able to tell just watching the flow vector get updated. Good. Okay, so now we just have to prove the lemma, but we're almost done. Okay. The claim is that the distance from S to V never decreases, or any V. Okay, so suppose I augment along a path from S to T. Okay, see where this goes. I want to show that no levels decrease. Okay, we're going to do this by induction on the level after updating the residual graph. Okay, okay, so what's the base case? Yeah, which is what's level equals 0? Level equals 0, that's only S. S will never change. Okay, okay, so let's do the interesting case. Okay, so good. We have some particular vertex. I'm looking at some level beta that's greater than 0. Okay, so let's say this vertex has level beta after the update, after the augmentation, and it has some level alpha before updating. So I want to show that beta is greater than or equal to alpha. Okay, and as a first step, there's some shortest path from U to V, right? And let U be that preceding vertex in the second graph. Okay, so that means the level of U is going to be beta minus 1. Okay, good. Okay, now, okay, anyone want to take the next step? We're closer to done than you think. Yeah. I think so. Okay, so I wrote beta equals 2 minus 2 for some reason. Hope that's not an issue. Okay, so level U had to be at most beta minus 1 before augmenting, right? Because it can't go down. Okay, so what does that tell us? Oh, okay, so let me give me a second. Um, okay, so if by contradiction, I assume that alpha is greater than beta, okay? But I know that U needs to be somewhere over here, okay? Because I know that U had level beta minus 1 or less by induction, okay? So this edge would be going backwards through the layers if it was even there, okay? So definitely V to U was not on the augmenting path, okay? Uh, and that means that U to V was in the residual graph before augmenting. Because we know U to V is in the graph after, and we didn't use V to U before in the augmentation. So U to V had to have existed before as well. Okay, good. All right, I think we're very close. Does anyone want to punch it home? And then you're off to spring break or your last midterm or whatever, you know, onerous day you have ahead of you. Get just one punchline. Yeah, so the level of V, and this is all like happening before the augment, has to be at most the level of U before plus 1. So I guess it's at most beta. Okay, so that's what we wanted to show. Right, so alpha is less than equal to beta. Okay. All right, I feel like I lost some of you. Or maybe you're tired, maybe it's about to be spring break. Okay, so, but that's it. So the point is if you do the shortest thing and you break it down slowly, then you'll show that the distance will never go down. Okay, good. So I think that's it. So that's the Edmonds-Karp algorithm. If you keep routing along the shortest path from S to T, even with bizarro fractional values, you're going to get to strongly polynomial time of m squared n. Right, and it came from this very sophisticated analysis where he focused on the number of hops from S to V for every vertex V, even though it's not clear what that has to do with our problem. Okay. Good. So I only want to note there's some historical significance. So before the Edmonds-Karp paper, people were quite happy with the Ford-Fulkerson algorithm. They just ran it. It was simple. It was, take a path, add the reverse, even with weird fractional values and stuff. They hoped that these pathological examples wouldn't appear. Um, but the Edmonds-Karp paper will make an argument in there. Hey, we should try to get strongly polynomial running times. That's important. Okay, so historically, this algorithm is also kind of important towards this argument of why we should try to get polynomial running times instead of, this like m times lambda sort of running time. Okay. Same Karp. Yeah, so Karp was a kind of ahead of the curve in So both Karp and Edmonds were historically really at the forefront of arguing we should try to get polynomial running times and making this distinction at a time when not everyone was making I mean, they barely had like vacuum. I mean, computers were so primitive, not everyone was looking so far ahead. Yeah, but trying to identify polynomials, saying no, exponential is not good. Something that depends on the output value is not good. That was not an obvious argument back then. It might not be an obvious argument anymore now, right? Now that we kind of shifted back to a lot of these empirically different algorithms. Okay? But still, that's a different conversation. So I want to note the historical significance of Edmonds-Karp. They also had a weekly polynomial running time, which was actually guessed earlier, and that's going to be on your homework. So you'll have some spring break to find that out. Okay. All right. I guess we're all tired. It's spring break, so have a good one.